Hello everyone. In this video we look at the concept of coordinate covalent bond or the dative bond. Now what is the coordinate covalent bond? So if you have a normal covalent bond, right? So what is the understanding we have? Let us say we have a covalent bond between the two atoms A and B. So A is the atom from one element, B is the atom for the other element. Okay. So what is the normal covalent bond concept? A will contribute one electron for the sharing, B will contribute one electron for the sharing, and that is what is going to form a single covalent bond. So this is what we will be calling as a single covalent bond. Okay, so this is the normal covalent bond. But what can be also happening is the both electrons of that shared pair, right, can be contributed by just one atom. So both the electrons of that sharing between the two atoms can be contributed by just one of these atoms. It is not like, atom A has to give one electron, atom B has to give one electron. It can also be possible that, let us say we have a bond between C and B. Okay, both the electrons of the bond can be given by just one element, C in this case. So such a covalent bond, right, is what we call as coordinate bond or the dative bond. So what do you call it as? Coordinate covalent bond, or in short we can call it as what? Coordinate bond. What is the other name for this? We can also call it as dative bond. Now when we look at the dative bond here, the way we look at it, we do not see that both atoms are similar. In a way, what do we see? C is giving both the electrons for the bonding. So we will say that C is what? Donor. So the atom that is donating the pair of electrons for the bonding is called as what? Donor. So here one thing we need to keep in mind carefully. It is not like the electrons of the C are taken away. Electrons of the C, let us say for example C is having its own lone pair of electrons. Where it is going to give the pair of electrons? It is going to give it from the lone pair. So the lone pair of electrons as it is will be given for the sharing. That is it. So it is not like the electrons are lost by C in this case. Electrons are still controlled by C, because the shared pair is also counted for the respective atoms, right? The only thing is, without even contributing an electron, because of the shared pair, right, B is also going to be getting what? 2 electrons. So in terms of the overall count of electrons, for B it will be like what? We will see a 2 electrons addition, because without even, normally what happens? Shared pair means one electron will be coming from each of the atoms, like that. But here, without giving an electron, B is getting a shared pair, right? Which means what? The net change for the B, what is the electrons net change? It is what? 2. Whereas in the case of C, previously these 2 electrons are the lone pair of electrons of C. Now what is happening? They are in the shared pair. But is there a change? There is no change in the overall electrons of C. That is not going to happen. So whenever a normal covalent bond is formed between A and B, what is the overall gain in the count of electrons? Each atom is going to gain 1 electron, because shared pair will be counting for both the atoms, isn't it? So we'll count the shared pair for both atom A as well as atom B. But in the case of coordinate covalent bond or the dative bond, what is the difference you see? The donor here, in this case, C we are calling as donor. So donor will have no change in terms of its overall count of electrons, but the atom which is accepting the pair of electrons for sharing, we will call it as what? Acceptor. In this case it is B. The acceptor is going to have a change of how much electrons? It will have a change of 2 electrons, because without even giving anything for the sharing, it is getting a sharing pair, right? Which means the net gain will be what? 2 electrons. And to make it clear as to which is the donor atom and which is the acceptor, right, we can sometimes even use arrow to indicate the coordinate covalent bond. So arrow will be pointing from the donor to the acceptor. Like in this case, what we can say, from C we can put an arrow towards B. Normal covalent bond means what? We'll just, so between A and B we have a normal covalent bond, means we'll put a bar, that's it. Here we can put an arrow. Arrow will be from where? It will be from the donor to the acceptor. So one thing we need to keep in mind is that here this is not a complete transfer of electrons. The donor atom is just sharing one of its lone pair of electrons with the other atom B, that is it. Okay. Now once the coordinate covalent bond is formed, from the study of the bond as such, right, there is going to be no difference between a coordinate covalent bond or a normal covalent bond. That is the reason why once a bond is formed, right, we can even, it is not like always we have to represent this with an arrow. We can also represent the coordinate covalent bond also with a normal line, but the only thing is we should know that this is a coordinate covalent bond or a dative bond. So as such, right, once the bond is formed, it will be indistinguishable from a normal covalent bond. Properties wise, it is not going to be any different. Okay, there also we have a shared pair, here also we have a shared pair. Properties wise, it is not going to be any different. Okay, now when we look at one of the very classic examples of this coordinate covalent bond, right, it is the case of ozone. So in ozone, right, the 3 oxygen atoms do not form a ring shape. See, normally if you look at the ozone, right, we know that we have 3 oxygen atoms, okay, and each oxygen has a covalency of 2. What is the covalency of each of the oxygens? 2, which means each oxygen has to form 2 bonds. So what is initially thought of is, could ozone exist like this, or could it have a shape like this, where you have a ring where each of the oxygens, let us number them, no? So oxygen 1, you can see it is forming how many bonds? 2 bonds. Oxygen 2, it is forming 2 bonds. Oxygen 3 is also forming 2 bonds. So we are able to satisfy the covalency requirement of each of the oxygens. But experimentally what is found is that ozone is not having a ring structure, it is having an open structure. Then the only way we can explain the existence of ozone with an open structure is with the help of the coordinate covalent bond or the dative bond. Okay, so how we can explain the existence of open structure of ozone using the coordinate covalent bond concept. So first what we'll do is we have 3 oxygens, right? Open structure means what? It should be like this only. There is no ring, means we should have the 3 atoms bonded in that particular order. So which means, let us say this is the central atom. Okay, now peripheral we will call it as what? Oxygen 1, oxygen 2. Central atom, if it has to satisfy the covalency of any of the peripheral atom, let us mark this, it should form a double bond. It should be forming what? Double bond with the peripheral oxygen, oxygen 1. If it is forming a double bond, means peripheral oxygen covalency requirement is completed. So this is done. But what is happening is, since the central atom is also oxygen, right, what about the covalency of this? That is also completed. Now will it be able to form any more normal bonds? No. Then how this third oxygen will be able to exist in the molecule? It has to exist, means there has to be a bonding with the other atoms, right? Without the bonding it cannot exist. So this is explained by using the concept of the coordinate covalent bond. How? Now look at it. After the formation of the double bond with one of the peripheral oxygen, the central oxygen will be having, so it is given 2 electrons for the bonding here. So normally we'll just focus on the central oxygen. Central oxygen will have how many electrons? 6 electrons in the valence shell. 2 are given. What is the remaining number? It is 4. 4 means 2 pairs of electrons. Okay. Now look at the other peripheral oxygen. One of the lone pair of electrons will be given for the sharing. So here this peripheral oxygen is having 6 of its own electrons. This is not putting any electron for the sharing. The sharing electrons are contributed solely by what? They are contributed solely by the central oxygen. Now as a result, what is going to happen? Look at this. So we have the 2 shared pairs here, that is there. One lone pair still remaining on the oxygen, another lone pair is given for the sharing. Okay, so with the oxygen 2 in this case, is oxygen 1, that is oxygen 2. So what you see here is, this is what we are calling as the coordinate covalent bond. Now as a result of it, if you are counting what is the total number of electrons on that peripheral oxygen atom 2, what is it going to be? It is having 6 of its own electron, plus 2 electrons are coming because of the shared pair. Totally what is it? 8. Now look at this oxygen, central atom oxygen, it is not going to violate octet. Why? Because it is having 4 electrons here coming from the 2 shared pairs. It is having 2 electrons of its own, and this shared pair also we have to count, means what, 4 plus 2 plus 2, what is it, totally 8. So this is how we'll see that in ozone we can have the coordinate covalent bond between where, between the central oxygen and one of the other peripheral oxygen atoms. So look at it. So we have the central oxygen, this is central oxygen, right? So the central oxygen is already formed two bonds, double bond with another oxygen, okay? So this valency is also, this covalency is completed, but how it can still form bond with the third oxygen, coordinate covalent bond. So you can see here this pair, right? What is it? It is fully contributed by the central oxygen. So how we can write the bonding in ozone? We can write it like this, okay? So the double bond, and this side there is a coordinate covalent bond. So this is the donor and this is the acceptor, okay? So this is what we see in the ozone. Later we will see here, see the Lewis diagram that we are representing here is only to indicate how the sharing of electrons would happen. Later when we go to the valence shell electron pair repulsion theory, we will even talk about what will be the shape of the ozone molecule. But here what we know is it's an open structure, okay? So later we will see that the actual shape of ozone molecule will be a bent shape. So what will be the shape of the ozone molecule? It will be a bent shape. We'll study about it. But this is about the coordinate covalent bond or the dative bond in the case of ozone. Now similarly we can talk about other examples also, like SO2. Same story. Sulfur, it has formed a double bond with an oxygen, means sulfur octet is also completed, because sulfur is having what, 6 electrons in the valence shell. This form covalency is what, 2, right? After forming a double bond, sulfur covalency is also completed. But still how the sulfur will be bonded to another oxygen? With the help of a coordinate covalent bond. You can see the sulfur, it's forming a double bond with one oxygen, okay? Now it will be having two lone pairs. One of the lone pair will be given for the bonding with the second oxygen. So as a result, what you will see, sulfur, there is a double bond with one oxygen, one lone pair will remain on it, and this is the coordinate bond, okay? That happens in the case of SO2, okay? So same will be in the case of the SO3 also. So again, here's SO3, sulfur, it forms a double bond with one oxygen. Here the sulfur covalency requirement is completed, but there are two oxygens which have to form actually double bond. But here how they can achieve the octet? Through coordinate covalent bond. So without even contributing any electron, the sulfur has got two lone pairs, right? So one pair will be given for sharing this side, another pair will be given for sharing on to the other oxygen. So this is about the, we can see in this visualization, right? Sulfur, so here it is forming a double bond. So these are, you can see we are indicating the electrons of sulfur with a cross, so that we can clearly understand how the contribution is coming here, right? The shared pair is only coming from sulfur. Here also the shared pair is only coming from what? Sulfur. The oxygens, they are not giving any electrons. So these two are what? Coordinate covalent bonds. This is a double bond, normal double bond, okay? So here also we can see this side we have what? A normal double bond. One electron is coming from oxygen, one is coming from sulfur. But here you see these bond electrons, they are coming only from what? Sulfur. The bond electrons are coming only from the sulfur part, okay? So this is how we have the coordinate covalent bond. Now coordinate covalent bond, if you understand in simple terms, right, it is able to make an atom to participate in bonding. See, in this case sulfur has already reached octet, but still sulfur is able to participate in bonding without violating the octet rule, isn't it? Because of coordinate covalent bond formation, there will be no net change in the number of electrons of the particular atom. So whatever is our donor, right, donor will not have any change in the net number of electrons. The change will be only for the acceptor. Acceptor will have how much change? Acceptor will be having a change of 2 electrons, because without even giving an electron, it is able to get one shared pair, right? So the total change in the electrons for the acceptor atom will be what? 2. Donor, there will be no change, okay? So we can look at some more examples. The case of hydroxonium ion. So what is hydroxonium ion? It is H3O plus. So what is H3O plus? We can also call it as what? Hydronium ion, okay? So H3O plus, what we have is the oxygen is bonded to two hydrogens. Okay, so now it will be having what? It will be having two lone pairs. Okay, so H plus means what? It does not have any electrons. So the lone pair can be used for forming a bond with the H plus. So thereby what are we having? We are basically having a coordinate covalent bond. You can see the H plus coming and we can say adding onto the water molecule. So H2O is what? This is water molecule, right? So the H plus is adding onto water molecule, and what is the bonding that is happening here? The oxygen atom is giving, you can see the oxygen, right? So here this side it is a normal covalent bond with this hydrogen. This is a normal covalent bond. One electron is given by oxygen, one is given by hydrogen. But look at this now. Both the electrons are given by, so this is the H plus that is coming. Both the electrons are given by what? Oxygen. This is what? The coordinate covalent bond or the dative bond. Okay. So in terms of the overall molecule charge representation, how do you represent? Remember what we keep saying, the charge will be taken onto the overall ion. Like this we will represent H3O plus. Okay. But we can see this bond will be what? It is a coordinate covalent bond. And as I said, once we look at the bond formation, once it is over, we will not be able to really distinguish between what is an coordinate covalent bond and what is a normal covalent bond. Similarly, if you look at the bond formation between ammonia and BF3. So ammonia and BF3, right, they will be adding on to each other. And the addition that is happening between ammonia and BF3, right, is also through the coordinate covalent bond formation. So boron, it has formed bonds with 3 fluorines. We have discussed about BF3, it's an electron deficit molecule. Okay, so boron, after forming the bonding also, the total count of electrons on boron is what? Only 6 electrons, electron less than octet molecule. So in case of ammonia, nitrogen has formed 3 bonds with hydrogen, it is having a lone pair. So the lone pair can be donated to form a bond with boron, and here nitrogen atom is acting as the donor and boron is acting as the acceptor. We can see this bond, right? This is the bond that is between the nitrogen of ammonia and boron of the BF3. Okay, so this bond is what? It is a coordinate covalent bond. Look at this question. Explain the existence of CO molecule based on the coordinate covalent bonding. CO means what? We have a carbon and we have an oxygen. We have to explain the existence of this molecule based on the coordinate covalent bonding. See, first of all, if you have a carbon and oxygen, so what is the covalency of oxygen? Oxygen has got a covalency of 2. What about the covalency of carbon? Carbon has got a covalency of 4. Means normally oxygen octet requirement will be met if oxygen is forming a double bond or 2 single bonds. Carbon octet requirement will be met when carbon is forming 4 bonds. It can form in 2 double bonds or 1 triple bond, 1 single bond, or all 4 single bonds. It can form 4 bonds by any means, but the thing is it has to have a covalency of 4. Now how do we achieve it? If you think about it, right, if the carbon and oxygen are able to, because they can only form bonds between them, isn't it? Because there are no other atoms available. If the carbon and oxygen are able to form a double bond, imagine what is going to happen. The covalency requirement of the oxygen will be completed, that's it. But still the carbon is short of 2 more covalency. It is formed only 2 bonds, right? It has to form 2 more bonds. How this is going to happen is, so if you have the carbon, so look at it, so we'll put cross for the representation of the electrons of carbon. Okay, so carbon, it has given 2 electrons, so 1 2, that's a double bond. Okay, remaining electrons of carbon are what? It will have 2 of its own electron, that is the lone pair. Oxygen is having oxygen is given 2 electrons for the bonding. Total valence electrons of oxygen are what? 6, right? It has given 2 for the bonding, means it will have 4 of its own, 2 lone pairs. Now the thing is, carbon covalence requirement is not completed, so one of the lone pairs of oxygen, right, will be donated for forming a coordinate covalent bond. So look at this carefully, what is going to happen? Carbon, okay, and here we are getting the third bond. Observe this carefully. Third bond electrons are given only from where? Oxygen. Third bond electrons are given only from the oxygen. Now look at it, the total electrons of carbon after the formation, this is what? This is the coordinate covalent bond. So here we have 1 lone pair of electrons of carbon and 3 shared pairs, 3 bond pairs. Totally what is it? Shared pair can be also called as what? Bond pair. So lone pair means 2 electrons plus 3 bond pairs means what? 3 into 2 electrons. Totally what is it? 2 plus 6, 8. So thereby the carbon is able to reach the octet. What about the oxygen story? By donating the lone pair of electrons for the sharing, oxygen is not going to have any net change. You can see here. So oxygen means we have to count it, right? So now 2 of lone electrons plus what is the number of shared electrons? 6. So totally what is it? The count of electrons for oxygen is also what? 8. Thereby carbon is able to reach the octet and oxygen is also able to reach the octet. So what is the representation we can think of? Carbon will have double bond with oxygen, and the coordinate covalent bond will be from the oxygen atom to the carbon, because oxygen is the donor. Oxygen is what? Oxygen is the donor and carbon is the acceptor. So this is how we will explain the existence of CO molecule based on the coordinate covalent bonding. But as we said, once the bonding is formed, then what we will say, we will not be required to always represent the bonding with the arrow. I mean, if you want, we can represent. Otherwise, we can even represent it like this. But what we need to understand is the third bond is what? It is a coordinate covalent bond between the oxygen towards the carbon. Okay, so this is how we can explain the existence of the CO molecule based on the coordinate covalent bonding or the dative bonding. So this is what we need to learn with regard to the coordinate covalent bonding, and we will see in the next video.